welcome to this afternoon's keynote session. This session is being delivered by from the Boston University Neuromuscular Research Centre. I think you'll find it an exciting session to watch. I believe that Carlo De Luca will be telling us about the controller motor units. I don't know about the rest of you, but I've often wondered that the EMG can sometimes be a rather crude method of gaining information on data, that maybe only the temporal information is useful, but this is really exciting. This tells us how we can decompose that signal down to provide lots of detailed information about the muscle and its function. I'm certainly looking forward to this session. I hope you'll enjoy it. Okay, so I'll hand over to Professor De Luca. Thank you very much.
Thank you very much. This is my first participation in a meeting of the ISBS, and I want to tell you all that I'm delighted to be here. I haven't had much of a chance to see some of the other sessions, of course, with notable exception of this morning's participation that I attended with great delight, but I will in the next couple of days. So I'm looking forward to being a participant from the receiving end rather than the giving end. I wish to thank the organizers of the Congress and the members of the Executive Committee of ISBS for inviting me to be here. And I would like to point out in particular Antonio Veloso, because it was through his contact and friendship that brought me here. So Antonio, if you're in the audience, thank you very much. If not, I will tell you that later. All right, so I'm going to speak on a topic which I perceive is going to be quite different than those that you have normally heard or may hear for the rest of the sessions at this meeting. It deals with the business of trying to understand how muscles are controlled. Now, I don't have trouble associating that issue with the general concept of biomechanics. Others may, but hopefully by the end of this session here, I will have convinced those of you who are skeptic that you need to understand something about how the central nervous system and the peripheral nervous system controls muscles to make force. And when you have force, you have movement. And when you have force, you have all those wonderful things that occur to the bone matrices and the rest of the tissues in the body. So think of this talk here as a talk that describes or tries to describe how it is that force is generated in the human body. And I will speak to individual muscles. I will ask the question as to how do we control the motor units in one muscle, so that the wonderful things that happen with force occur. And how is the system organized? And more importantly, the focus of my discussion will be on how it is controlled. It is impossible for me to remove myself from that. I am within my DNA an engineer, so I need to think about things like control. All right, I have the good fortune of having done this work with a delightful associate of mine, Paola Contessa. Is Paola in this room? Paola, you're not here. Well, this is Paola. I thought she'd be able to stand up. Anyway, I'm sorry? Oh, so the work was supported by funds from the National Institutes of Health in the United States and also from a grant from the Italian government. We are an equal opportunity taker. We have no borders to the people who we allow give monies to us. So let's begin. The first thing I wanted to review a couple of things with you, just to make sure that we're all on the same page before we delve into the question in more detail. The fundamental unit that generates force within a muscle, as you hopefully all know, is a motor unit. A motor unit is a group of muscle fibers, all of which are connected by branches of one motor neuron, the cell body of which is in the anterior horn cell, which is a particular part of the spinal cord. If an excitation occurs in that cell body in the spinal cord, it travels down the motor neuron, it travels down all the branches, and it reaches all the muscle fibers that are connected together as a motor unit. Each of the muscle fiber generates a little force twitch. The motor unit as a whole generates what we call the motor unit force twitch. That motor unit force twitch is the fundamental force unit in the human body. You cannot, under voluntary control, and by the way, I am only going to speak about voluntary control. I need to underline that because I am going to make a proposition today which will disagree with information that has been learned in the past about what happens when you electrically stimulate nerves and look at the force production in muscles. But anyway, that is the motor unit force twitch is the fundamental force unit of the muscle. And this picture describes that. There's the timing of the action potential. Here's the force twitch that occurred. And if I repeat that continuously, you see the motor neuron is firing, force twitches occur, and because it's firing fast enough, I have a superposition of these force twitches, and this is known as tetanization. That is, the force, it no longer is individually distinguishable from the individual motor unit force twitches. That occurs, as you, I'm sure, well know, when the time interval between firings is less than the time duration of the force twitch. Can you all hear me in the back? My voice tends to go down with time, fatigue, you know. When it does, please let me know. Because I get involved with what I'm saying and I can hear myself very well, so I don't have a problem. Okay. Now, how are these things repeated? That is, how are they controlled? Here's a schematic, just to help us along for review. This is a cross-section of the spinal cord, out of which come motor neurons. This is indicated as number 1. This is the nth one that goes to the one muscle, and this is, one in between something. The force twitch, which I've just spoken about, that corresponds to this motor unit, the first one, is generally among the smallest, and the force twitches of those associated with a lateral recruiter motor unit is generally amongst the largest, and in between there is more or less a hierarchical progressional relationship in the amplitude of the force twitches. If now I activate the system, that is, I say some voluntary message is sent to this level of the spinal cord, things will happen. Motor units get recruited. You know the Henneman size principle. The smallest ones get recruited first. The latter get recruited at the end. And so let's see what happens. So here it is, the first one being recruited first, down here. And this is the force switch, and the force increases as this firing rate increases. You notice it's firing faster here than there. That means I have increased the excitation at this point, and I have increased the force output. These are the locations where each of these were recruited, and this is the force associated with this motor unit, this without motor unit, and this one without motor unit. Now, I'm giving the story away by this image, and I have a little test for you at the end, because if you understand this slide here, you can go home right now. Okay? Well, you don't have to go home, but you'll understand the rest of the talk. All right, so the issue before us that I want to present is the following. How does this work? How are these motor units controlled? And specifically, I'm going to speak about the firing rates. That is the rate with which these pulses fire. Is there an order there too? Is there an order among the firing rates? As Henneman showed us, there is an order among the motor unit recruitment size. Okay? So that's the question of the day. Now, about 50 years ago, Eccles and colleagues postulated that we should expect, although he did not observe, that when you under electrical stimulation, he found that the higher threshold motor units, that is the larger diameter ones, when stimulated, had what he designated a shorter after hyperpolarization period. That is, the distance from here to when the potential goes back to near zero was shorter for the high threshold motor units, that's the latter recruiter motor units, than it was for the early threshold motor units, that's the lower recruiter motor unit. And on the basis of that, he made a postulate, which was strongly supported by Cornell and many other people since, which you have probably studied in your classes, and I suspect some of you may be actually be teaching this in your classes. And that was the following, that because the after hyperpolarization period, that is the time during which an actual potential cannot repeat itself, is short for the high threshold ones, therefore, teleologically thinking, they ought to be able to fire faster, right? Because the time interval between is short. And inversely, that the earlier recruiter motor unit, which by the way, and according to these diagrams here, has a longer hyperpolarization time, cannot fire as fast, and therefore their firing rate would be lower. Now, this was not proven. This was a postulate, but it became dogmatic. In fact, it became part of the canon of physiology. And you can pick up any book right now on this matter, and you will see that story. So we asked the question, and by the way, the argument that supported this argument was that, why not? Should it not be so? If you can fire faster, then you can tetanize. Remember what I showed you before? The motor units. And when you tetanize the motor unit is when you get the most force out of that motor unit. Of course, logically, it would mean that the fast, high threshold motor units would fire faster and then would generate a lot of force. And that would be very force efficient for the muscle. Conversely, the lower ones would not, but it doesn't matter because they have a small force twitch, so they don't. Who cares? Well, and in fact, this was called the optimal matching between firing rates and the force twitches of the motor unit. And the underlying concept in all of this, not mentioned but implied, was that the central nervous system is so organized so as to maximize the force capability of a muscle. Isn't it beautiful? Okay, this of course is the same thing that Platonic thinking said about the Earth moving around, the sun moving around the Earth. But then Galileo looked in a telescope and found otherwise. So let's look into a telescope. What are they saying? This is just a slide that summarizes what I've said. The motor units, starting from the smallest to the largest, have shorter hyperpolarization. So the first one were to fire. There's the force. This is the firing rate of that. This is the force twitch, and here's the resulting force that it contributes. Then the next one were to fire. It would fire faster because it's larger, has a higher force twitch. Multiply that by that, and you get even more force. And then the very last ones at the end are even faster firing. They're even greater motor unit action potential, and boy, oh boy, Look at the good stuff that they produce. So this is the way you would maximize the force output of the muscle. Now, the question is that true? It's tempting to agree with it logically, because why would not the central nervous system, after millions and hundreds of millions of years of going through the process of organizing itself to control motor units of the muscle, not be organized in a way so as to maximize the force output of a muscle? It seems so obvious that that should be so. We asked the question, and we developed a technology to try to answer the question, and I will spend now about 4 or 5 minutes on the technology, but that will not be the center of the talk. I want to talk about what we see with that technology. The technology which we have been developing for many years is called EMG signal decomposition. And what basically we can do, we can put a sensor on the surface of a muscle, record the surface EMG signal. Through very sophisticated algorithms, we can decompose this signal here in the individual motor unit action potential trains, which comprise, that is, which forms the surface EMG signal. Now, it took a long time to develop this technology, but what it does, it provides you with a map of the firings of each of the motor units. And here is a cartoon only. This is only a pictorial example where we in fact have taken the action potential of motor units and determined through this process here precisely where they're fired. And this is the case for another motor unit, and so forth and so on. What you can see is that these, in fact, are the data that come from the peripheral nervous system here through the central nervous system to the muscle. But when they are seen with this sensor here, as you're all familiar when you look at it with a surface EMG signal, they get all superimposed and messed up, and you can't tell what's what. We can now provide you with a map that actually formed that signal. By the way, if you linearly add these, you will get that signal there. All right. We can do this with an accuracy of about 95.2 on the average, ranging from about 89% to 98%. And we know when there is an error. So we know which motor units we can look at with a very high degree of accuracy. This is published work. There's a paper in 2006, one in 2010. There is actually another one that's come out in 2010. There's one to come out in press in about 3 months, and there will be a couple other ones after that. So this is a well-documented technology that has undergone some, shall we say, rigorous reviews by people who cannot read and write and are deaf and dumb. Now, it's a revolutionary technology. It will naturally meet questions, and we enjoyed responding to those questions. This is the technology that, as it exists today, the sensor is rather small, as you can see it there. We have a circular sensor here. Now we make them oblong, but it's the same thing. The detection is done by these 5 pins, which sit 5 millimeters apart with one in the center. It is amplified through the system here, and the software, the algorithms reside in a small computer. And it produces outputs of this kind here, which I will describe in more detail. This is a typical example, I would say. The system looks at, through those 5 pins, it actually generates 4 channels of differential EMG signals, which you see at the top. So these are the signals as they are detected by differential combinations, 4 differential combinations of the sensor. This is just an expanded epoch to show you how complicated this signal is. In this signal here, I believe, I'm not sure, but I believe it was recorded from the first dorsal interosseous during about a 35 to 50% MVC contraction. The force is indicated by the black line. This is the force which the muscle generated. You see this contraction of being approximately 30 seconds long. And what you see inside here, there are 30 individual motor unit trains, each representing a specific motor unit. And the bars represent the time at which that particular motor unit fires. This is the shape of the actual potential of that motor unit as it is extracted from this weather mess. And this provides you simply with a better view of what this condensed presentation is. Now, when we have this information, now we actually have the firing pattern of several motor units, in this case 30, we can sometimes do more, during the same contraction. These are co-active motor units. So this is what's really going on inside the muscle. As the muscle is performing this contraction here. Now, there are more than 30 motor units involved in that contraction. We, in this particular example, could only see 30 of them. But 30 is a hell of a lot. It sure is a hell of a lot more than stimulating one motor neuron, as was the case when the original hypotheses that we will discuss were made. So we can do this over and over again, many different contractions. The restriction on the technology is that the contraction must be isometric. That is, the length of the muscle cannot move much, but it can be at any force level. We can do this up to 100% MVC. Now, what I want you to appreciate is this slide here, because although these bars, which show the time in which motor unit firing, are very interesting to look at, they don't really provide us all that much information, not in answering the question that I have posed. So I'm going to do a little transformation here. I'm going to go from these firing times to firing rate. Firing rate is how often does this thing fire? How many pulses or bars per second are occurring? So this is a motor unit here, which is firing thusly. Here is a second motor unit gets recruited at this time here and continues to fire thusly. I put on top of this a mathematical filter. Don't get too worried about that equation. It's a simple cosine filter. You can just pull it right off the web. But there's a reason why we use this particular filter. I don't think it's important to discuss at this time. But what it does is that it provides you with a number over telling you the number of firings that occur within its window. And then you move this along, and this number progresses thusly. So you get a curve that describes the firing rate of the motor unit. Think of it this, if you were to listen to this, you hear it gets a little bit faster. And that's what this is. It's like if you have a BMW, you look at the speed, you have a tachometer on there. If you have a Cadillac, and you look at the speed, you see this. I don't know what it tells you in the car. But, so it really is just the analog transformation of a digital representation, which is what these firings are. This is what I want you to keep in mind, all right? So this is the firing. And what we can tell visually is that this one here is firing faster than down there. Why? Here's the rate, the axis that describes the rate. And you can see it here with your eyes. There are more pulses per unit time here than there are there. And both cases, as you move time forward, the number of pulses increase. That's what this does. This curve is higher than down there, and both increase with time. That's what we're going to be using as our parameter. So let's go back to that contraction which we had before. And these are the firing rates that I would have gotten from those timings. Now, there's a lot of information here, and it looks very messy because the system is noisy. The neuromuscular system, and when it produces the firings of motor units, it does so noisily. There's a reason for that, a rather good reason. But let me just clear it up for you. Remember that filter that I talked about? I'm going to make it wider. That is, it's going to capture more pulses per unit time. And you see how the curves are getting a little smoother? It's 1 second wide right now. I'm going to make it wider again. You see how you're starting to get and I'm going to make it even wider. Okay, I don't have to, not sure, but you see? So this is the same data, just smoothened more and more and more. But this tells you something rather interesting. The first recruiter motor units, the ones that occur at the time, have the higher fine rate than latter recruiter motor units. Remember, this is the force. So this one here is recruited at this point, and this one is recruited at this force point. For all of them. There's a beautiful hierarchical progression going from the early recruiter motor units, the one with a large force twitch, which are firing slower. But not just that, everything in between is proportional. There is a rule in this system that causes this to happen. Now, what's important about this point here, this is precisely the opposite of what Eccles and Granit and Kendall measured. Now, were they wrong? No. Because what they did is they electrically stimulated the motor units, and they made the high threshold ones far faster. But under voluntary control, they do not. If you were to electrically stimulate this motor unit here, at the bottom, which are firing slowly, it can fire fast, but not under voluntary control. So it has the physiological capability to do that, but that capability is muted under voluntary control. Now this has implication in terms of what happens when you do exercise, because I'm going to make an argument that this is so for all muscles and under almost all conditions. Now, at the end of the talk, if you have a few minutes, we'll talk about how you can cheat a little bit. You might be able to change this to the advantage of increasing the force output of the muscle as a consequence of exercise or medications. Now, what I can do is I can mathematically describe those curves, and I can go through a process of this kind here, and I'll be very brief about this, but basically, these are those fine rate curves again, and I can fit these red lines to them. And these red lines are negative exponentials, 1 minus e to the minus x something. And if I keep changing the time constant, the rate at which this rises, I can match the early ones that rise fast and go high, and the latter ones that rise slowly and stay low. And the equation that describes all that is very messy, but it's basically of this kind here. Lambda being the fine rate, and the fine rate is a function of time. Obviously, you can see that with your eyes. This is time, and the fine rate is changing as a function of time, but it's also changing as a function of phi, which is the force level. This contraction reaches higher values than other contraction. It also changes as a function of the recruitment threshold, when at the force level at which it's recruited. And all of that is captured by an equation of the form of this kind here. And when you put in all the parameters, it becomes a little tricky. But let me show you what happens when you plot that equation. You get this. These are two muscles. Now these equations, these curves are plotted by equations that describe the curve, the fine rate curves that I have shown you before. What I've also added here is the distribution of motor unit recruitment. This is for the first dorsal interosseous, this muscle here, and this is for the vastus lateralis, which you probably all familiar here. Very different muscle. One small, one large, different fine rates, very, very different muscles. Now, this motor unit, the FBI, recruits motor unit up to about 60-65%, and then increases force only by increasing its fine rate. Not so for the vastus lateralis, it does so to about 90-95%, but this one recruits most of its motor units near the first 10% of the MVC, maximum voluntary contraction, where this one here has a much more gentle distribution. And what you see on the left is this motor unit also contains about 120 motor units. That's been well documented. whereas the vastus lateralis has about 460 or so. On this curve, we've shown you every 10th one, I believe. Where this is the first one, this is the last one, and here it's every 10th one too. This is the first one, and this is the last one. Now, what you see is a very harmonious hierarchical progression over here. Still, the mathematics that we have adapted from the real data show that the earlier recruited one always far faster than the latter recruited one, be it here or be it in this muscle. Even though the distribution of the motor units among them differs. Yeah, I like to whine. It's not going to work. It's not going to work. Okay. Fine rate range varies across muscle. The vastus lateralis is a little bit higher than the FDI. Fine rate excursion is exponential. All those functions you saw were exponentials with progressively different. The time constants of the fine rates, that's the speed with which it rises, decreases for the increasing recruitment threshold. That is, the higher threshold motor units are shallow in rise, whereas the earlier recruiter motor units are rather sharp in rise. And so here's the first point I want to leave with, what we call the onion skin property. At any net excitation level, and at any time during a contraction, early recruiter motor units have a greater fine rate than latter recruited ones. Alternatively, it can be stated as the fine rate of a motor unit is inversely proportional to its recruitment threshold. If I were to put a line through here at the excitation level of 40%, that line will cut through the values of the fine rates of each one of these motor units, and those would be the ones which you would see. Another way to think about this is, how much time do I have? 15 minutes. How much? 13. Let's skip. This is another way of thinking about it. You can think of it as a vat that has spouts. When the excitation gets to a certain level, you have one motor unit firing. When it goes to a higher level, the second one. But it's at a lower distance, lower fine rate. And you can continue to do this, and you get this progression. This is an analog of how the central nervous system is set up, the anterior horn cell is set up to excite the motor units to go into one muscle. This is no different than the curve which I've shown you before. All right. Now, what does this mean? Let's go through this rather quickly. It says that what the after hyperpolarization hypothesis, which I said before, said that small motor units have the higher fine rates, which is not what, have the lower fine rates, smallest twitch, generate a force, then the next motor unit have higher fine rates, and so forth. This was the after hyperpolarization hypothesis. But if you do that, what I left out, and what everybody else seemed to not have included, is that fast, high threshold motor units, if they fire fast, they fatigue earlier. They fatigue earlier. That's what this is supposed to indicate. The force cannot be sustained and comes down. So the summed force of the muscle is like this. You can generate a lot of force, but you can't sustain it. So if that were true, we probably wouldn't be sitting here today, because we'd never gotten away from the tiger millions of years ago when we were evolving. The onion skin hypothesis says the small ones fire fastest, the medium ones fire less, and the high ones fire slowest. Now, what's the problem with this thing? The problem is that you don't tetanize the high threshold motor units. So the force output is going to be noisy. But you can sustain it. You can run away from the tiger, get to a tree or whatever, a hole, go home, have fun, and your DNA continues. Okay? All right. So now we have produced all of this into a model. This is a little complicated. Do not get overwhelmed by the side. Look at me, listen to me, okay? So here's the force level. This is the pattern that we just talked about. You're not familiar with this spectrum. These are the force switches that we're going to describe that are in the force switches that are in the motor units of the muscle. This is the output force. This is the target force. And here's a feedback to try to keep this force, the output of the muscle, to be the same as the level of excitation. So this is an experiment that you would do if you wanted to have a constant force isometric contraction fixed on a screen while you're making a contraction. What has to happen? We know that this changes. The force switches of motor units as they fatigue. They potentiate and then they go through diminution. So there has to be some sort of an adaptation in the force in excitation level to make the force output constant so that it's equivalent to what you want to maintain. I'm not going to go through the process other than to say that we know how to describe the force switches mathematically, and because I don't have much time, you just say, very nice, very nice. Let's do it again, very nice, very nice. Okay, I can do this. So I can describe the force switches. I also know, by some measurements which we made in our own laboratory, that what is well known in the literature, in fact, is true. We agree with it. The force switches, this is the first small contraction. About half a minute into the contraction, the peak increases and then they continue to decrease. This is contraction time. This is force of the force switches. We can modulate, we can duplicate that mathematically. We can generate the forces of the individual motor unit with their force switches. You can see the higher threshold ones. This, by the way, represents the motor units in the FDI. This is number 120th, which would be the largest, the highest threshold motor unit. This is number 1, the first, which is the lowest threshold motor unit. Almost generates any negligible force, whereas look at the high ones. They do not tetanize. These come from our mathematics. So let's run the experiment. The excitation level is set at 20% right here. And here we're going to see the force switches. The number of motor units that are going to be needed to generate this force here is going to show here. And there's a total available of 120. And all the time factors of the force switch changes and final rate changes are already included into the mathematics of the model. And here's the case for the first 1/2 minute of the contraction. So here we are. This is the beginning of time, and this is 1/2 minute. Here's the force which is produced. You can see it's held rather nicely constant. This is the target force, the red line. That hasn't shifted much. And it took the first 91 motor units to fire to generate 20% MDC of the FDI. 91 out of 120. These are the ones that are still available. These are the ones which are active. These are the force switches of the motor unit on the left of that excitation line. Let's now go for the next 5. That's 1/2 minute, and it's gone up to 90. It's gone down to 90 motor units. It's lost 2 motor units. It de-recruited 2 motor units to maintain the force level the same. Why? Because they were potentiating. So they're generating too much force, and what actually happened, you could not see it, but this line moved left a little bit, deactivated 2 motor units. And here we are now. In the next 1/2 minute, right there, it's lost a few more motor units. There's 88 up there. We started out with 92, so this has shifted a little bit. You'll see this movement a little bit more. And now we go, that's up to 2 minutes. Now we go to 2.5 minutes. And you see now it's 89 motor units. And now we're going to let it run. And what I want you to see is the number of motor, see it's running. This is generating force. Look at this, it's increasing the number of motor units. That's shifted. Watch this line, it'll move gradually to the, so you see that? Gradually to the right. Now it's got 98 motor units. It's recruiting more motor units because the force twitches of the active ones are diminishing in amplitude. They're weakening, they're fatiguing. So it's recruiting other motor units. And the force is maintained rather constant. And here it goes, it's building up. It's now at 7.5 minutes. It's up to 113 out of 120. 8 minutes, 8.5 minutes, and boom. At this point here, it's exhausted. It's used up all its motor units, and the excitation has gone all the way to 100%. But because the motor units are fatigued, the force twitches have diminished, they could not produce sufficient force to generate what we originally said as 20% of the MVC and the contraction. And if you do this experiment on yourself, by the way, you go home and do this, it'll take you about 8.5 minutes. So here's what you saw. You saw that in the first 5 minutes, half a minute, pardon, these are the motor units which are active of all these available, and you can see that it de-recruited one. These are the fine rates of all the active motor units, of which there were 91 at this spot. This one is about halfway in the contraction, from 4 to 4.5 minutes. It has recruited many more motor units, 96, not many more, a few more, 96. And here are a couple of recruited ones. And then here's the end of the contraction, where it's starting to go crazy, and it's recruiting like mad until it runs out of motor unit. The reason these are higher than they were at the beginning, because the last motor units to be recruited fatigue very quickly, but they potentiate while they're fatiguing. That's why they have a high peak. These are the forces that you may not have paid attention to. At the beginning, the force was quite steady, more fluctuation, and this was at the end, more fluctuation. If you do this experiment, you'll find that these are the real data that we've actually collected, and these were the data that I had just synthesized. Not a bad comparison, considering this is nothing but a bunch of googly-gook mathematics, and this is a real muscle working here. Here's the experiment that was done, and here I'm going to leave you with some of the last slides. We actually recorded these data. This is the contraction that was sustained until they could no longer be held. This is the amplitude of the force twitch that was measured in the whole muscle, electrically stimulated muscle. It potentiates at the beginning, continuously goes down afterwards. Motor units first go down. These are the fine rates of the motor units, and then they start to rise, and more recruitment occurs. This is exactly what you saw in the model. Okay. This is what happens when you are right-handed and left-handed, but the same thing we can model when you have, if you were to look at the fine rates of motor units of muscles in your right hand as opposed to your left hand, if you're right hand dominant, you'll see that the fine rate to produce the same force here is less than it is there. Again, it's a function of the force twitches, which are higher because of the hypertrophied muscle fibers from a lifetime of exercise in your dominant hand. It's consistent with the model. All right, here's the last slide. What does this all mean for exercise? So I've told you one thing. I've said, first of all, that what Cornell and Eccles taught us half a century ago does not hold for voluntary contraction. I do not say the data is incorrect because those experiments were done correctly and the data was correct, but they looked at something else. What everybody else then did was interpret what they looked at from electrically stimulated severed muscles in rats to imply that that is what happened during voluntary contraction in normal, healthy human beings. And that does not hold. I've given you my interpretation, our interpretation of why that is so, and I posed a model that I believe explains what is going on in the muscles when they're generating contractions. But I've also said that the relationship between firing rates and recruitment threshold is fixed. I have not given you reasons to believe that yet. There's other information and data that we have in the process of writing. So you have to distinguish, because being in process of writing is not necessarily being in process of publishing. That will show that that is locked in. It's locked in if you're looking at the right hand, left hand, if you're looking at healthy people, if you're looking at diseased people, neuromuscular disorder people, you're looking at stroke patients, you're looking at Parkinson's patients. That is locked in. What isn't is what the mechanics or the muscle fibers are doing. They get altered by the diseases. As a consequence of that, the excitation point changes in the firing rate plane. And that's what people see. They report all these differences and different firing rates associated with different diseases. The different firing rates are associated with a force. It just takes a different number of motor units, the different kinds of motor units to generate the force which you want to have. So if it's fixed, what does it mean for exercise? Wouldn't you like to be able to get to the high threshold motor units of the hell? Don't mess around with that small stuff. You want force, right? You want lots of force. You want impulsive force. You want power. Can you cheat? Can you break that pattern up? And the answer is probably yes. We have some evidence right now, which is way too premature to talk about. But keep this in mind. I'll leave this thought with you. What you're looking at in those fine rates are filters. Each one of these motor units filters the information that comes from the central nervous system different and responds differently and responds with a different time constant. Filters can be manipulated. Electrical engineers do that for a living. So there might be ways of manipulating the force, the excitation scheme, so that the force response will be different, even though the structure, that is the onion skin structure, is not disturbed. We're exploring that right now. And the objective is to involve the higher threshold motor units more in the force generating business than they would be otherwise under the kinds of contraction which I showed you were all just linear force increasing contractions. That's all I actually showed you, are those examples. So, can it be done chemically? Are there medications that you can induce in the anterior horn cell to have some soma, some cell bodies of muscle of motor neurons respond more or less? I believe so. What happens during concentric and eccentric contractions? What I've talked about were isometric constant force contractions. The technology we have can follow some eccentric and concentric contractions. We're not doing that. I wish someone would. Because it would be interesting to understand if the control remains the same during eccentric contractions in comparison to the concentric ones, which are the ones we commonly see. Can you change the feedback from spindles so that the excitation that they bring back to the anterior horn cell is diminished or increased, and therefore increase the net excitation without changing the voluntary activation? Can you make the muscle stronger, whether it wants to be or not, for example? All these things might be possible. All these questions we can investigate and possibly even understand with the technology that I have presented. So I wish to stop right here, and I thank you all for your kind attention.
Thanks for a nice talk, Carlo. I have a very simple question. In your fatigue protocol, you argued that after a while all motor units are used up, and that's when the muscle fatigues and force goes down. How do you know that all motor units are used up? How do you know that the muscle might not keep some in reserve for exceptional circumstances?
Well, of course, we know from the model that they're all used up, but the model is designed to work that way. The question I suppose posing is not what actually happens in reality. So I'm not in a position, from what I have seen to date, to be able to answer that. I can only tell you my belief, but not facts. The concept of having reserve motor units that are coming to play some other time it is one that I've thought about for a very long time. I have no evidence of that in the natural world. Others who have argued this point have not provided what I was convincing evidence for me. Because until you tell me what the force is doing from the muscle, and these things are going on, we need to kind of have a serious discussion. However, the concept of reserve motor is usually brought up with the question that you talked about now. The mother about to see a child run over from a car and jumps in front of the car and lifts it up to save the baby, things that she could not under any other circumstances do. You don't need to have reserve motors to do that. What you need to have is some hormonal release of some kind that activates that changes the electrical characteristics of the high thresholds of the anterior horse side, so they can fire fast. And then you can generate an enormous amount of power, which you do not normally do under voluntary control. So if you want to think of a reserve in that kind, that I'm happy to sort of, continue the discussion on, because I believe that's possible, because we know the reserve is there in that fashion. And this is why in tornado, it might be possible, in fact, to increase the force output through chemical interventions.
I'm afraid we'll have to stop at that point because we're running short of time and we need to change over to other sessions. Before doing so, I'd like to present Carol with this